All right, welcome back, everybody. We're going to be talking about thermodynamics today. This is intended to be a review, not necessarily any instructional, but reviewing all the concepts associated with thermodynamics and the way I approach them in my AP Physics 2 class. We'll look at these three things. That's how I'd break it down. But then there's going to be some extra stuff, including entropy, which we won't be talking about necessarily specifically here. We'll talk about it at the very end. And some heat transfer ideas as well. Most of us are aware because chemistry is a prerequisite for AP Physics 2, but you've exposed yourself to the ideal gas laws, and that talks about our relationships between pressure and volume, pressure and temperature, and volume and temperature. So those are the ideal gas quantities. You could also be taking into account the number of moles, but generally for our purposes, we keep this value constant. So I eliminate it from our ideas. The way we would want to be approaching this is, through the three main gas laws, which will ultimately concern ourselves with the ideal gas law. But we want to look at how the pressure is related to volume, how the pressure is related to temperature, and how the volume is related to the temperature of an enclosed, isolated system, meaning no particles can flow in or flow out. So the ones that are fairly straightforward is things expand when they heat up. So we find a direct relationship there. If the temperature were to double, the volume of the substance would also double. Given that we keep the pressure constant, all of these require you to keep the third variable constant in order for these to work effectively. We find that the relationship between pressure and temperature is also direct. I use this alpha for relationships. And then as you increase the volume of the container, the amount of collisions that the particles have are fewer, so the pressure of that system goes down. So we find an inverse relationship between a pressure and volume. Given that we keep the other two, we keep everything else constant when we write this statement, we were ready to write our ideal gas law, which only works with ideal gases, not real gases. But in an introductory class such as AP Physics 2, chemistry, etc., you would only deal with an ideal gas. Then we find the ideal gas law is just PV equals nRT. You can then start doing a few things with it. This is the combined ideal gas law. We will keep these two values constant all of the time. And as a result, as long as we have a closed system, that's why we're keeping this constant, we would find that the ratio of the pressure times volume divided by temperature is equal to a constant. So pressure times volume divided by temperature equals nR. So if we have that at location 1, as long as we keep this value here constant, we'll find that the pressure at volume 2, or pressure at the second measurement, the volume at the second measurement, and the temperature at the second measurement are also equivalent. So this technique this is useful in solving some thermodynamics problems because we're going to be keeping the pressures. We can relate the pressure at location 1 to the pressure at location 2 because we are keeping the amount of molecules constant. Just so you know, this would be the moles of our gas. This is the ideal gas constant. And we for our purposes, we use 8.31. Pressure, we use pascals, which is a Newton per meter squared. For volume, we use cubic meters. And for temperature, we use Kelvin. To keep that in mind in our approach to solving the rest of these questions. So here's how we would use our ideal gas law. We would compare some things. But we apply that in our AP Physics 2 class using a PV diagram. So a couple of things before we get to PV diagrams. I want to talk a little bit about the ideal gas, the laws of thermodynamics. We talk about the zeroth, the first, and the second. There is a third law. It's just relatively undiscussed because it's common sense in my book, but so is the zeroth law. If it states that if A and B are in thermal equilibrium, meaning that they have reached the same temperature, etc., and B and C are in thermal equilibrium, then guess what? A and C are in thermal equilibrium. So that's the 0th law with the idea of thermal equilibrium. Transitive property of math or something like that? I don't know. The first law says energy can't be created or destroyed. I'm going to run out of space, aren't I? You've heard this since junior high. Hopefully you were paying attention or listening. We talk about that as U, the amount of internal energy something has, is equivalent to the amount of heat it has plus the amount of work done on the system. So we use this as the first law of thermodynamics, which we'll be using in our problem-solving techniques when we're doing PV diagrams. The second law of thermodynamics is written lots of different ways. Ultimately, it says the disorder of the universe is increasing. And we use the word entropy to measure the disorder. So we want to be aware that the entropy of the universe is always increasing. And that just says that in any process, generally heat is generated. Therefore, we cannot be 100% efficient in any process that we do. And the third law says the entropy, let's think about it. I got to go back to my chemistry days. Entropy of an object that approaches absolute zero has a zero entropy. Has no entropy. Meaning that at absolute zero, all motion of all molecules stops. So it doesn't have any disorder. It's all exactly where it's supposed to be. It's a very clean, neat space. Sorry that you're muted. I'm recording this for YouTube and I didn't want anybody to be there, but at the end we'll have conversations. It's good to see some of you, or at least observe that some of you are here. I'm sorry. So those are the laws of thermodynamics. We focus mainly on these two to solve our problems, and then we sometimes are asked to describe what happens to the entropy of a system. So keep that in mind. 0th law, thermal equilibrium, AB, BC, A must be C. Energy can't be created or destroyed, and we use the idea of first law of thermodynamics right there. The disorder of the universe is increasing. We think about entropy there, and then just extra accoutrement, something unnecessary, and use for that. Okay, so there's your laws of thermodynamics. Finally, let's get to a PV diagram, do some problem solving stuff. This is generally how I think of all thermodynamics, and it's a puzzles that we got to solve. Sorry about the squeak. I don't know if that picks up, but we have pressure and we have volume. And then I just draw a line. We'll call this A and we'll call this B. Before we get any farther, we'll say that we go from A to B, sorry. But I want to make sure that we're aware of a few things that we can do here. Obviously, we could read the pressure and the volume at any location by reading the graph. We could identify the slope of this line. It's 0 in this case. But most importantly, we could also find the area under the curve. And as a result of finding the area under the curve, you would need to find that. This is an algebra-based course, so they should be relatively geometric shapes, or you should have enough information to find it. But this right here is the area. Well, what does the area tell us? Well, the area is going to be a base times a height. And in this case, the base is volume and the height is pressure. So we want to think about what the heck would pressure, the base, or the height, excuse me, times volume be? What is pressure times volume? Well, pressure is a force per unit area, as discussed earlier in our fluids discussion. And volume is, I don't know, how about an area times a length? Meters, 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 or length times width times height, something like that, volume. And as a result, when we take this idea of pressure being force per unit area and volume as being three-dimensional shape, we will find that the areas reduce and we're left with a force times a length. And relating that back to mechanics from your AP Physics 1 class or AP Physics C class, you would find that to be equivalent to work. So the area underneath the pressure volume graph is equivalent to the amount of work done on the gas. So now we're ready to define the statement. And we want to say that work is the area underneath this graph, but is also equal to negative P delta V. The negative comes from because in AP Physics, we define the work done on a system, not the work done by a system. Occasionally, they get those backwards and inside and outside, but we want to make sure we're doing work done on a system. Some of the descriptors that we make later on make that a little bit more obvious as we continue. So the work done on a system, in this case, we see that it goes from A to B and it expands. So we would say that the gas does work to the environment. So it loses energy would be the approach that we'd want to, we would say that it expends its energy to the universe. But we'll talk about all of that here shortly. So we got our statement of work. We're also going to want to bring into this a couple more things. We want to bring in our idea of first law of thermodynamics. The internal energy of a system is equal to the Q plus W, Q being heat added or removed. If it's added to the system, we make it positive. If it's removed from the system, we make it negative. Work as defined here. And then we also want to be aware of our ideal gas law, our combined law, PV equals nRT. And then there's one last one that I'd like to think about in my class. This comes from my chemistry background. It's not necessarily listed on your formula chart. These three right here are listed on your formula chart. However, this one is not. Because we deal with monatomic ideal gases, I define the internal energy of a system based on 3/2, the coefficient for an a monatomic gas is 3/2 nRT. This deals with the interactions those molecules could have with one another. I'll take this as an aside, as an opportunity to talk about temperature of a system is related to the average kinetic energy. So we want to think about this temperature right here being proportional to the velocity of the molecules squared. That's from your kinetic molecular theory concepts in previous years. So these are my tools for the problem solving that I use. Work, internal energy, relating heat and work, our ideal gas law, and internal energy defined in terms of moles temperature. I find this to be an effective tool to solve every problem that could be there, although it requires that we solve for heat at the very end. I don't have a direct way that I talk to my students about identifying the heat. That would be your like MC delta T if you wanted to add heat to a system, but that's not necessarily the approach that we take in AP Physics 2. Some terms that we also need to be aware of, just some nomenclature. I like to use PV terms. I like to use isobaric a lot. I like to use isothermal. And I like to use ISO, what do we want to call that last one? Isovolumetric, sometimes referred to as isochoric. Occasionally, although it doesn't appear to be in our scope and sequence for physics 2, a term of adiabatic could show up. What you need to be aware of with all of these is that isobaric defines one of these variables over here very effectively for us. It defines that the change in pressure is equal to 0, meaning that as I go from location A to location B on my PV diagram, I find that there's no pressure change. This looks like a horizontal line. We'll discuss. Isothermal relates the temperature, and it says it does not change. So we find that the change of temperature is 0, which takes care of a few things. Note that the temperature is the only factor that affects the change in internal energy. Isovolumetric, well, that was pretty obvious. Delta V equals 0. When you have an isovolumetric process, you have no work done. Note that we have taken care of pressure, volume, temperature. There's our temperature. We've taken care of U and found that relationship. There's only one variable here that's not accounted for, and that's adiabatic, and that takes care of Q. So that Q is equal to 0. That means no heat flows into or flows out. And that immediately should let you know that this is an impossible scenario, an idealized scenario, if you will, because I can't make a perfect insulator to allow heat not to be transferred into or out of a system. I guess you could run the system in outer space, but that's a little bit more expensive. Okay, so those are some terms that we'll be using. I guess I could put these there too. I don't know. Sometimes people might not be aware. So I'll put expansion and compression. With an expansion, we want to talk about delta V is positive, is greater than 0. And with compression, we want to think about delta V being less than 0. What this allows us to do is quickly identify this word here as an expansion or compression, and immediately define how much work is done on the system, whether it's a positive value or negative value. How does that look? The problems that we do in my class, or that we do in AP Physics 2, look like this. I'll keep our tools listed. And the approach that I take is with a diagram. So we have a pressure volume graph. Let's draw a process here. We'll again have a horizontal line, but in this case, I'll go from A to B, moving to the left. I would define this type of process from A to B, a thermodynamic process. We can look at diagrams of those, and I'll provide some questions for us to look at in Google Classroom. This is an isobaric compression, to use some of that nomenclature from before. What you can do with this information, and why I find so much joy in PV diagrams, is the plethora of questions that can be answered with just this phrase. We want to have our 6 variables that we would be thinking about. So PVT, that's from our ideal gas law, but then we also want to be aware of work, heat, and our change in internal energy. So what I ask my students to do is identify what's going on with the pressure during this cycle, or this not cycle, excuse me, just this step, and we identify that the amount of the change of pressure is 0. That's the isobaric. Notice that the vertical value of this graph does not change. We identify what's going on with the temperature, and we can do a few things to know that it decreased, but let's do a little bit better job. And we'll say that the volume of this decreased. So we'll put negative. And because the volume decreased in our first statement from the ideal gas laws, the individual ones, we find a direct relationship between volume and temperature. So we know that to be negative. Now what we can do is use these tools that we've been able to pull from this graph just by observing it and reading it, interpreting it, however, whatever verb you want to use, and then relate it to these other variables. So we can, over here, we can go, what's going on with the work? Well, the work is proportional to negative P delta V. Since we know that the volume is negative, we think of this as being negative. Pressure is always a positive value. The lowest pressure you could have is 0, and that's difficult to do. You can have a negative pressure differential, a vacuum, but you can't necessarily have negative pressure independent on its own. We just have a change in pressure that's negative. So this value here will always be positive. And then we take a negative times a positive times a negative, and we find that we had to do work. The environment did work to the gas. It squeezed the gas, squeezed it. We're going to get to Q at the end, but we can look here at the T. The joke in my class is the two main universities in our state are Texas and Texas A&M, and they don't necessarily get along well. So the way we talk about it is, if you're a Longhorn fan, you would say U is proportional to T, and if you're an Aggie and a Texas A&M fan, you would say that T is proportional to U. That comes from this statement right here. And if you want to really think about what we're doing, we're saying that the change in internal energy is proportional to the change in temperature, just a delta being there. We've identified that the T is negative, therefore the U is negative. And the final piece of this puzzle is, how would you identify what's going on with Q? Did we add heat or remove heat from the system? As a result, we go over here and we say that since this is negative, why did I say 0? Oops, that's positive. A negative times a positive times a negative is a positive. Oops, my apologies. We would say that since we have a positive value here, get rid of these now. A negative times a positive times, yeah, okay. We find this to be positive. We find this to be negative, which means in order for us to go from A to B, we had to remove a significant amount of heat to do this problem. This works with any thermodynamic process that we do here. Ideally, you want to keep one thing constant, and in this case, we kept the pressure constant. Alternatively, you could draw a line vertical, which keeps the volume constant, and then go through this same process. Don't ignore these right now. That would be an isovolumetric process. You could do an isothermal process. This line would be 1 over V. P is proportional to 1 over V, so we have an inverse relationship there, hence the curve. And then I keep that there because an adiabatic process would be similar in shape and only identified. You wouldn't be calculating anything. It would actually drop a little bit lower for that to be the case. Now, obviously, they can expand or compress. They can go left on the graph or right on the graph. And that's how we would use this right here to take care of any of those problems. A couple of more things that you might want to think about while you're looking at a PV diagram is you may want to identify quickly by inspection where the temperature is high and where the temperature is low. So we put the pressure, we put volume, and up here I would put hot And down here, I would put cold. And this is the point when a student will tell me there's no such thing as cold, and I go, I am aware. So for them, I tell them it's not hot. So down here is cold when you have low pressures, low volumes. And up here is high temperatures, hot when it has high pressures, high volumes. T big, T small. So something to think about there when you're doing PV diagrams is you can easily determine whether the internal energy increased or decreased if you have just a line that trends from left to right or from bottom to top. All right, PV diagrams, thermodynamics. Okay. Occasionally by inspection, they ask you to do a few things for it, and I want to talk about a cycle now. And the cycle can look lots of different ways. I generally do nice geometric shapes. In this case, some type of rectangle. And a question that occasionally throws students off is the work done during this cycle positive, negative, or zero? So let's draw it. I don't know. Let's say it's a clockwise cycle. Couple things you want to be aware of when you're dealing with a cycle is delta U for a cycle is equal to 0 because I start and end at the same location. All right. So if we started A, we go all the way around. We could talk about here, the temperature increased. Here, the temperature decreased. Why is this arrow pointing this direction? Temperature increase, temperature decrease, temperature decrease, temperature increase. Using that previous trend, we could talk about no work in these isovolumetric steps. And we could talk about an expansion and a compression. So the question I have is work going to be for this cycle? This cycle, is it going to be positive, negative, or 0? So we want to find the amount of work done on the gas from A to B, and we want to look at the amount of work done on the gas from C to D. So from the work from A to B, I'll use the area underneath A to B, and I'll shade it with red. Notice that's a rather large rectangle, and it's an expansion. So during an expansion, we'd say that with negative work, this value here would be negative. But C to D, a smaller rectangle, is a compression. And we would see that we have a purple color now. This doesn't mix as well as I want it to, but you'd see that the red and the blue have opposite signs. So the amount of area from C to D actually is just canceling out. They are the same amount, just with opposite signs. And the only amount of work that we need to concern ourselves with for the cycle is just the area inside of the rectangle. And we see that the expansion takes place at a higher pressure than the compression. So for this, we would say the work for this cycle is negative. Since the work for this cycle is negative, and we use the first law of thermodynamics, U equals Q plus W, in order for us to have a no change in internal energy for this cycle with a negative amount of work done on it, we have to find that in order for this to take place, we have to find that the Q is added to the system. And as a result, that makes this type of process, in this case clockwise, a heat engine. Or basically, we add heat to a system to do work on work. The most common of this is a combustion engine. You can feel your engine after you've driven for 50 miles. You'll find it to be relatively hot. You also find that the efficiency of your engine isn't great, but it served us well over time. So that's clockwise. The inverse of a heat engine would be a refrigerator. And that says clockwise. It just says clockwise. But the reverse cycle, a refrigerator would operate counterclockwise. And that would be a refrigerator where you do work to cool the gas. And then you might ask, well, how is the entropy inside the refrigerator decreasing? Or how does the air conditioning here in Texas decrease the temperature of my house? Or how does the air inside my house cooler, but the entropy of the universe is still increased? In order to make things colder inside of your refrigerator, inside of your house, to remove heat, you have to put it somewhere. So if you go stand next to your air conditioning outside, or if you were to touch the back of your refrigerator, you would find it to be quite hot. So the net increase or the net change in entropy for the entirety of the universe is still increased. You have to think about what's going on, flowing into versus flowing out of the system. Ideal gas laws, laws of thermodynamics, PV diagrams with heat engines. All right. Lastly, this formula is referenced on your formula chart, and we talk about it. And, this is where you bring up those three main words about heat transfer. And then you give yourself the chance to think, oh yeah, heat transfer, you got conduction, convection, and radiation. One of these is the most effective way to do it, and that's through touch conduction. Convection is how I make my macaroni and cheese, and radiation is how the Earth has temperature. But for the most part, we focus on conduction in this class, and we want to think about what's the most effective way for us to conduct not electricity, sorry, I'm getting ahead of myself. What's the most effective way for us to conduct heat? And you want to think about how would you want to do this, and you have to first think, well, what's going on with those molecules? Well, those molecules, hotter molecules move fast, and less hot molecules move more slowly. So as a result, we have collisions that would take place between something that's not hot and something that's hot. And as a result, the heat is transferred from hot objects to cold objects. Make sure I'm looking at something correctly and using the terminology that they'd like. And of course. So that's what we want to think about. What you want to do is you want to make sure you increase that contact area for that conduction to take place. So if you want to cool down your GTX 2080 Ti, you have a heatsink that's placed on it. You also have a fan that's circulating the air. So in order to effectively transfer heat, you want large surface area. You want the rate at which heat is transferred. You want a large delta T, so your hot thing and your cold thing have a big temperature differential. In addition to that, you want to have a material that has, a specific heat that is conducive to this. Aluminum has a low specific heat and transfers heat rapidly. So you want to think about the material you're dealing with. And let's see, we were talking about the rate at which heat is transferred. Okay, so now we can relate these. The rate at which heat is transferred. So we got heat being transferred, and we've got time. That's what makes it a rate. And then we think about Would a large surface area play a role? Would a large change in temperature play a role? And would the material play a role? Those are the things that we can change and manipulate to determine all of this information. Oh, I forgot about one thing, how far it has to transfer between the two, the, the, the distance between the two. Okay, so we take material, we're going to give it the letter K. We got area, surface area, just going to call it A. And then temperature. And then this distance between them we'll call length. Typically, that would be the length of the material, whether it's air, aluminum, steel, glass, etc. If you're thinking about keeping your house cool during the summer or warm during the winter, the material that your glass is made out of, it makes a difference. And how thick it is would play a role. Okay, so the material, just a constant. You look it up in a data table. It would have to be provided to you, or you'd have to have enough information to find it out. The area, the contact area of the two different temperatures, the amount of different temperatures they are, so how hot the hot is, how cold the cold is in Kelvin, notice SI units, and then finally the distance that it must travel. The length is an inverse relationship, and that would be the rate through conduction, the rate at which heat is transferred between two objects in contact. It depends on the material, the contact area, the difference in temperature, and how far or how close they are to each other. That's a good review of thermodynamics. Obviously, the questions ask you some different ways to use that information. But I would say that gets you a head start. I'm going to be opening up another meeting here shortly. You can find the link for that in Google Classroom so that you can ask further questions or just whatever you need, we can discuss. But with that, I wanted to say I can't wait to see all of you graduate. I hope that you have a great rest of your day, and I will see you soon.